All right, in today's optimization question, we're going to look at a Norman window question. So in this question here, we've got, you have yourself a Norman window. What a Norman window is. It's a rectangle, and it has a semicircle on top. And what they want us to do in this question is they want us to find the dimensions that will give the greatest light. So under a certain constraint, and the constraint they gave us is the perimeter is 24. So essentially you want to maximize the area of the shape given a perimeter of 24. So let's go ahead and draw this Norman window. All right, so a quick sketch of this Norman window. It's going to look something like this. And what they tell you in the question is the total perimeter of this object is 24. That's referencing the distance around the object. So the distance all the way around is going to be 24. That's the material we have to work with. We're going to assume in this question, we're going to assume that this does not have there's not like a piece of wood here for the window, just all on the outside of the window here. All right, so what do we have here? I'm going to label this with an X. I can label this with a Y. I'm looking to maximize the area of this shape. So let's get an expression to represent the area of this shape. So the area of this Norman window would be composed of a rectangle. That's this right here. And you can see here, that's easy to calculate. That's just going to be x times y, plus the area of a semicircle. Well, the area of a full circle, as we know, is pi r squared. Here, my radius of my circle would be the distance from here to here. That's exactly half of this distance. So in this case here, it's going to be x over 2 squared. So I am getting here pi x squared over 4. That's an expression for the area of a full circle. That's going to imply what I want is the area of half of a circle. So if I divide this expression by 2, you're going to get pi x squared over 8. So I'm going to go ahead and add that here. This is going to be pi x squared over 8. So now what I have here is I have a representation for the area. This is what I want to maximize. But again, you can't maximize two variables. We have to maximize one. So I need another constraint. The constraint they gave me was the perimeter of this object is 24 feet. So I need an expression to represent the perimeter. I know it's going to equal 24, the perimeter, but how do you write the perimeter? The perimeter here is going to be the distance around the object. Well, this is x, this is y. So right away I know I have x plus 2y. I just need to find an expression for the distance from here to here. Well, the distance from there to there is a semicircle. So if we take a look here, the circumference of a full circle is 2 pi r. Since in this question the radius is x over 2, I can replace r with x over 2, in which case I get pi x. So that represents the circumference of a full circle. I want half of a circle. So the circumference of half of a circle is going to be pi x over 2. So I'm going to go ahead and take that information. I'm going to add that to my perimeter here. So it's going to be plus, I'll dump that over there. This is going to be plus pi x over 2. All right, let's kind of reorganize this now that we have our two main equations. Okay, so we have our two equations here. This, again, to remind you, this is what I'm looking to maximize, but you can't maximize two variables. So what I'm going to do here is I'm going to first isolate for y in this equation. So let's go ahead and do that first. I'm going to substitute that into my area equation. So I have a function of one variable. So isolating for y here, I'm going to first multiply across by 2. That'll give me 48 is 2x plus 4y plus pi x. And again, isolating for y, I'm going to get 4y is 48 minus 2x minus pi x, in which case y is 48 minus 2x minus pi x over 4. I'm going to go ahead and substitute this back into the equation. Substituting this back into the equation, we can eliminate the y and change it to a 48 minus 2x minus pi x over 4 plus pi x squared over 8. And now I have a function in one variable. So now that I'm here, I can go ahead and distribute my x value and divide that by 4. And this will be pi x squared over 8. So now I have a function in one variable of x, and this is what I'm looking to minimize. So I'm going to go ahead and take my first derivative here. Okay, so I'm going to pop the 1/4 out of this expression before I take my derivative. So I'm just kind of taking the derivative of these piece by piece. So this is going to end up being 48 minus 4x minus 2 pi x. And then taking the derivative of this, again, the power rule kicks in. You drop down that 2. We can simplify that 8. That'll be pi over 4x. Right, so therefore, a prime at x, distributing the quarter, I'm going to end up getting here 12 minus x minus pi x over 2 plus pi over 4x. So again, looking to find these critical points here. There are no values where the first derivative is undefined, but there will be an x value where it is 0. So I'm going to go ahead and set this equal to 0. We can simplify this up a bit. I can see here that negative pi over 4 plus pi over 4 is going to end up being minus pi over 4. X is 0. Isolating here, I'll bring the x's to one side. And then I can collect these up a bit. If I collect these up, I'm going to get 4 plus pi over 4x. And solving for x here, I get my critical point of being 48 over pi plus 4. And now I have my critical point here. All right, now that I found my critical point here, let's make the following observation. The original function a at x, our area that we're looking to maximize, it's actually a quadratic. And if you examine this a bit further, you'll find it's a quadratic that opens downwards. So what I found right here is my critical point. I found this value right here. So I have found the max area. The endpoints to this function are just going to end up yielding areas that are 0, right? Either it's going to be like x is going to be too small or too big, and either way you're going to end up getting an area of your Norman window that is 0. So the answer, which is my only critical point, is x equals 48 over pi plus 4. So that's the width that's required to create a Norman window that will emit max light. Thank you.